Okay, the next section will be about distillation columns. I would say it's a very important section. There's some references here that you can also consult. So it's the textbook, Process Technology Equipment and Systems. But I think the most important one is on unit operations and instrumentation by Gary Janssen van Vuren. Some notes you will find in a PDF format just below this slideshow on my tutor. So if we look at the distillation columns, I would say the main important thing here is the separation process that actually that you can achieve with the distillation column, and that is relies on the principle of relative volatilities. So the speed in change, the principle of different boiling points. Then also further, it requires a sophisticated multivariable control. So the produced products of highest quantity and purity and produce the products at the lowest cost. Two very important terms that's associated with distillation columns is your dew point and your bubble point. So when the vapor starts to distillate, that is usually your dew point. So that's when it starts to turn again from a vapor into a liquid. And bubble point is when the liquid then turns into a vapor. Okay, let's use the following example for a basic distillation process. So a very basic production of methanol and ethanol. Okay. First, what we'll need is a sugar wash. So a sugar wash is a mixture of water, sugar and yeast necessary in the fermentation of alcohol followed by distillation using a still. So we're just going to look at again, as I said, the basic system. How can we actually then separate after we made the sugar wash? How can we get the ethanol and the methanol out of this mixture? Now, what's important here is temperature. Okay, so the temperature is very important. So for methanol, it will usually boil at plus minus 68 degrees Celsius at atmospheric pressure. Then again, for ethanol, it can boil and turn into vapor at plus minus 78 degrees Celsius. And that's also again at atmospheric pressure. Now, this atmospheric pressure is important because if your pressure is going to increase, it means that might then shift, because if the pressure increases, there's more pressure on the surface area of that liquid, and this in turn then is going to cause a higher boiling point. Okay, so if it's at atmospheric pressure, it will be at plus minus 78 degrees Celsius, and then water boil, of course, at plus minus 100 degrees Celsius. So you can see here, if we can control the temperature of a mixture, we can in actual fact then extract this vapor, okay, that will actually form at 68 degrees Celsius or 78 degrees Celsius or 100 degrees Celsius, and those are the components we then supposed to get. So let's just quickly look at what is methanol and what's ethanol and what could be the uses for those two components. So it's easy to get a sugar wash. Eventually, it's just sugar and yeast that will ferment for a certain time, okay? And that is then to produce then this methanol and ethanol in that mixture. So eventually, if we look at methanol, it's just a non-drinking type of alcohol, okay, which is mostly used to create fuel, solvents, and antifreeze. So it's a colorless liquid, it's volatile, flammable, and unlike ethanol, poisonous for human consumption. Ethanol, on the other hand, is an important industrial chemical. It is used as a solvent in the synthesis of other organic chemicals and is an additive to automotive gasoline. Ethanol is also the intoxicating ingredient of many alcohol beverages such as beer, wine, and distilled spirits. Okay, so if you closely look at the different components that one can actually get, this is maybe after a little bit of reworking here and there, one can actually produce solvents for paints, varnishes, perfumes, fuel for vehicles, alcoholic drinks, and also for the preservation of certain foods. Okay, looking at the different equipment that would be associated with a simple process like this, remember now that we have different boiling points. Okay, So if we can actually boil our mash, in this case it will be the sugar wash, so that will be again the sugar and the yeast that formed eventually the alcohols that's inside that sugar wash. Now by controlling the temperature closely to 68 degrees Celsius, the first thing that you will get out of the vapor, out of this mash, will be of course your methanol. Okay. Then also what you can do is, if you then, after you extracted everything and basically the vapor stopped, you can actually move to a higher temperature, 78 degrees Celsius, and you can then collect your ethanol. Now that ethanol eventually will also stop, because it means that everything will turn into vapor. It will be cooled down. So looking at the different components, you have your mash that's inside the boiling pot. You need to control then the temperature very closely. That vapor will actually move into a cooling section. You can also see this as a heat exchanger then basically. It's just cold water that's actually moving through or a coil, over a coil, and then there's some heat exchange that takes place there, and that vapor then it turns again into a distillate. Okay. And now depending if it's at 68 degrees Celsius, meaning that then you will get your methanol. Then after a while you can move up to a higher temperature, you can get your ethanol from this, and by cooling it down in that heat exchanger. And then also called then a condenser. And that will all be collected then in the collector. If you go to a higher temperature, then you will start to actually also get water part of this. So again, it's very important to closely then control your temperature. Of course, it won't be how can I say, purified methanol and ethanol. So one must just be very careful for that, but it can be used easily for biofuel. Okay, let's just quickly look at the main components that's associated with the industrial distillation column. Now you can see that there's a feed in here. So the previous example I would say was just a simplified distillation process, and that is a batch process. So meaning that you have that amount inside the column itself, and that's it, and you want to process only that portion and separate then, as the example had, the methanol, the ethanol from one another. Okay, but now if you have industrial process, it will be continuous. So there will be a feed pump, a preheater, the column, okay, a condenser, accumulator, a reflux pump, and also a reboiler. Because usually these columns are fairly large. It can be quite a few meters. Now, the feed pump will actually feed the column. That is the mixture that needs to be separated. Then you have a preheater. That preheater is just there to make sure that you don't now allow a colder mixture to go into the column, and it might upset the whole temperature. Okay, so you always will have that preheater. Going into the column, this is where the whole separation process will take place. And then you've got a top product and a bottom product. Now the top product is going to be the vapor, of course, and that will go to the condenser. This is where you will cool it down and you will change the vapor again into a liquid form. Okay, so that heat exchanger will be a cooling heat exchanger. Accumulator is just for accumulating then the product. And then you usually have a reflux pump that you can actually let it flow back into the column to get even further purified, and then you can get your distillate off that. But then at the bottom you also have a reboiler, because constantly we need to then actually supply that temperature that's needed inside the column. So in the previous example it was simple, it's only one single temperature control, and we only want to reach, say for instance, that specific temperature. Same thing, reboiler here, heat exchanger, and then eventually getting that will be your bottom product. Okay, so if we quickly look at the slide, you can see there's certain variables that's very important that we need to measure. So we looked at the different components, but on these different components, of course, there's going to be some measurements and some control that needs to take place. So the flow temperature for the preheater is very important. Your flow that goes into the preheater, and then of course the temperature of the preheater, so that you don't cause any upsets into the column if you have a colder flow that might go into the column. So that temperature needs to be controlled closely, as well as the flow. The pressure and temperature of the column also need to be controlled. The pressure will have an effect. If the pressure increases, it means that basically your boiling point is also going to shift. Just to give you an example, if we're going to boil water, say for instance here in Gauteng, and we're going to boil water, say for instance at Mount Everest, that is a lot higher above sea level, the pressure, say for instance at Mount Everest, is going to be less on the surface area of that water. So it means that you will actually boil then that water at a lower temperature. Okay, so the pressure is very important in the column, and that can have a great effect on the temperature. And then you also have just the level and also the flow that you have on your accumulator to decide how much you actually want to reflux into the column, or how much you're going to pull off as your distillate. And then the last part at the bottom product, you need to monitor your temperature, your level, and your flow, so that you can also decide how much you want to feed back, recirculate into the column for further purification. Yes, and then of course the level there, that will decide then how much you actually want to let it go off as a residue. And temperature will have a great effect on the bottom product, this reboiler, heat exchanger, eventually to determine what is the temperature of the column. Okay, on the following slide, just to show you that the preheater is actually a heating heat exchanger. The reboiler is also a heating heat exchanger. Okay, so you need to heat up the feed that goes into the column, and also the reboiler, the bottom product, you want to heat it up. Here one can just see that with a reboiler, eventually if you reach a certain temperature, what's going to happen? Some vapor is actually going to start to form, and it will actually go through the condenser and it will be accumulated in the accumulator. As the process goes on, more vapor has actually been produced, and also the accumulator, of course, you will have a larger top product. More feed is added to the column, so eventually you can see that your accumulator level is increasing. So again, larger vapor condensation that actually takes place, and then you get the separation of the different components. And this is how the process then continues. Again, more vapor, more distillate in the accumulator, and eventually you're starting to get the separation process and a better purification because of the reflux, and also the reboiler, maybe again feeding back some of those components into the column. Okay, yeah, just to give you another example, two types of components. Say for instance at the bottom you can have octane, and at the top part you can have pentane, two types of fuels. So same process here. You can see that there's different boiling points. So the one is at 36.1 degrees Celsius at atmospheric pressure, and then the octane as 126 degrees Celsius at atmospheric pressure. So controlling it closely, not going above the 126 degrees Celsius. What will happen if we go above 126 degrees Celsius? It means that you'll have then eventually at your top product a mixture again of pentane and octane. So we want to keep it, let's say, close to that 36.1 degrees Celsius at the top of the column. So eventually to get then pulling off this pentane into the accumulator, and then purifying that by feeding it back, so we can easily then separate the pentane and the octane due to the fact that they have the different boiling points. Okay, on this figure here is just to show you inside the column. Usually you have some trays, and that trays has got some bubble caps and so forth. That's just to cause a further purification. So the vapor will actually rise up, it will cool down, and it can fall back again to the next level. The temperature, since this is a very large column, the temperatures is going to differ a little bit inside the column in the different levels. And this is just again eventually to get a better purification in the system. So the column is not just as we had in the previous, or I'd say the simple example, where you just had a chamber where you had your sugar wash in, and then you add your heat to that. So again, this is a more complex system, so you can actually have different components at different levels that you can also extract. Okay, I think at the end we will see that as an example. Okay, so the first process implementation diagram that I want to look at, that will be related to the feed. So this is basically the mixture that needs to be separated that goes into the column. So firstly, it's preheated. So there's a cascade control arrangement that you will see on the next slide. Okay, so let's start at the first section, the feed control. So this goes to the column. That's basically the feed. You can see again, if you go to your main components on the previous slide, you will see that you have your feed section. Now this is the control on this. So we said that the temperature needs to be measured and also the flow needs to be measured. And this is an arrangement of a cascade controller. So the outer loop or the primary loop is your temperature, and then the inner loop or your secondary loop will be your flow. And then you control then basically the heating medium that goes through the heat exchanger. Okay, so you measure what's the amount of flow, and then you decide according to that what is the temperature of the feed itself that goes into the column, and we adjust then just the flow through that heat exchanger. And you can see here that if the temperature is too high, what needs to happen? It means that the valve needs to close down. Okay, and what happens if our temperature is, say for instance, too low? What needs to happen? The valve needs to open on the heat exchanger to allow more heating medium that goes through, and the feed actually flows through this heat exchanger, and you have then your heat transfer that actually takes place. Okay, so in the previous section, we looked at basically your feed control. There you can see is your flow and temperature. Then in the blue circle, you can see the pressure and the temperature control of the column is important. So we're going to look at a few process instrumentation diagrams addressing then this pressure and the temperature control of the column. Okay, so the types of pressure control that we're going to look at is the venting of an inert gas with distillate present. And this is usually done before the heat exchanger, so take note of that. Then the venting of an inert gas with distillate present. This is usually at the accumulator. Column pressure control by throttling a condenser water. High column pressure control and a vacuum column pressure control. So these are 5 different, how can I say, strategies that you can in actual fact implement on the distillation column. Okay. Now inert gases. So with the first two, we're going to look if there's inert gases. What is an inert gas? It is a gas that does not undergo chemical reactions under a set or given condition. So it means that it will actually be part as a vapor inside this distillation column, but this is a gas that actually we want to get rid of, and it's not going to form that easily a distillate eventually. So we don't want this to be part of our final product or the top product. Okay, so if we have an inert gas, say for instance, present in our column, it means that somehow we need to vent it because it can actually have an upset in the pressure. Okay, but here we can just see that if we measure what is the pressure on the column, if the pressure is not too high, it means that the venting will not take place. And you will also have a wet condenser. The wet condenser just meaning that before it goes to the accumulator, so there will be a buildup of, in actual fact, distillate inside this condenser. So it means that the vapor is not just going to pass continuously through this condenser, it will be basically blocked by the valve that's connected there to PRC1. Okay, so by checking what's the pressure, we can then actually open the wet condenser. It will release some pressure in the column, or we can actually throttle the venting valve just to get rid of this inert gases that's present. And then the last part is just the level to check the level of the accumulator. If the level is not too high inside of the accumulator, it means some of that will be fed back into the column for further purification. Here we can see that if the pressure in actual fact increases, the way to release the pressures then is by venting some of this inert gases. So that will release the pressure, and also then creating some space inside the wet condenser by opening that valve that's connected to PRC1. Will also release some pressure then inside the column, so that we can still keep it to that known, or let's say boiling points that we want. And then if the accumulator is in actual fact the level rises to a certain set point, it becomes too full, it means that we can actually then release some of this through the accumulator, through the valve that's connected to LIC1, and it can then be fed off as a final product or for further processing. Okay, another method to actually get rid of the inert gases. Again, so that's not going to easily turn from vapor into a distillate, say for instance, that we want. So if there's a buildup of these gases inside a column, what's going to happen? The pressure is going to increase. So we monitor the pressure on PRC1, and then by monitoring that, what can we do? We can throttle open, or if the pressure is not too high, measured variable smaller than a set point, we can keep that valve closed on the accumulator. Okay. And then also with the water, we can see how much we actually need to condense of this vapor that goes into the accumulator due to that level that's actually measured on the accumulator. Here one can just see that to get rid of the inert gases, eventually your measured variable of the pressure is greater than a set point. It means that one can open that valve that's on the accumulator to release some pressure. Okay, and further, to release more pressure, say for instance on the column, if the pressure becomes too high, so if the measured variable is greater than a set point, it means that we can again open the valve that's on the accumulator, and we can also open the valve that's on the heat exchanger. So that's going to let more cooling water go through the system. So what will happen is then that vapor will actually turn into distillate, and also actually reducing then the pressure on the column. Okay, I think the next process diagram is fairly straightforward. So you can see that there will be an equal pressure inside the column and the accumulator. There's no obstructions really between, there's no valve in that line. So we measure what is the pressure on the column with PT1. The controller then see if the set point is greater or smaller. In this case, say for instance, if the measured variable is smaller than the set point, it means that less cooling actually needs to take place. So we need to actually, the column pressure is then too low. So by having less cooling effect, you will still have some vapor in the system, and that in actual fact will increase the column pressure. With this, you can see that if the column pressure actually goes higher, what do we need to do? We need to send through more cooling water so that you can quickly change the vapor into a distillate. Okay, so and that distillate will then cause again the pressure to drop, because we'll have less vapor in the system. Okay, on the next high column pressure control, we can see that we do actually have two lines that goes to the accumulator. So there's two valves. It's also connected to the accumulator. The one's connected to a heat exchanger, and the other is connected in actual fact to the accumulator, where we measure the pressure inside the accumulator. So we measure the pressure on PT1 on the column and on PT2 on the accumulator. So if it happens that the pressure actually rises too high, it means that what needs to happen then eventually is then you look at the pressure in the accumulator. If the accumulator's pressure is low and there's no vapor inside the accumulator, we can quickly release some of that pressure actually through the second leg. Okay, here you will see under normal operation, just to get pressure released from the column, the first leg that actually goes through the heat exchanger will be opened, okay, and just normal condensation will take place. Here you can see that both the two valves will be open, so it means that the pressure inside the column is high, and also in the accumulator the pressure is not too high, so it means that we can quickly release some pressure into the accumulator, and condensing will then just take place in the accumulator. So both the two valves can be open in such a case. So if the column pressure is really high, it means that we can still bypass the heat exchanger on the second leg, so that we can quickly release some of the vapor inside the accumulator. Then we'll just then normally just then condense. Okay, so the next strategy is just a vacuum column pressure control. I think what's important here is why vacuum. It just means that you will actually change the boiling points. So with a lower boiling point, less temperature will be needed. So if you think about the example of boiling water in Gauteng and boiling water on Mount Everest, by having then a lower surface pressure on the bottom product, it means that vapor can easily start to form at a lower temperature because of a lower boiling point. Now if you look at this, that there is no obstruction between the column, the heat exchanger, and the accumulator. Okay, so there's no valve there, so we assume then the pressures will be the same. So if you look at PT1, PT1 is measured on the accumulator. It could just as well be measured on the column. Okay, now if the measured variable is smaller than the set point, it means that with this vacuum system, eventually the steam actually creates then a lower pressure on that ejector. And by creating that lower pressure on the ejector, you can either wise lower the pressure inside the column, or you can use the outside air just to fill up on that lower pressure that you have on the ejector, and that will cause not the column pressure to be affected. Okay, over here you can just see that if it happens that the measured variable is greater than the set point, so it meaning that we need to drop on the pressure of the column itself, what can you do? You can in actual fact then release some of the pressure through the ejector, so the air supply will be cut off. Okay, on the next section, so we are done now with the pressure control. So there's a few strategies there that could be implemented. Then also we had looked at the feed control, where you had your flow and your temperature control in a cascade manner. So now we're just going to look at the bottom products control. So that is basically your reboiler, and that's adding the main heat to your distillation column. Okay, so if you look at it, as we said, we need to measure temperature, there's flow that we need to measure, and then there's also, of course, the level we need to measure. Now, if the measured variable of the temperature, say for instance, is smaller, so the column temperature actually needs to increase, what do we need to do? Again, with this cascade arrangement, the same as what we had basically for the feed control, the first process instrumentation diagram, you can see that by measuring that temperature, if the measured variable is smaller, it means that than the set point, we need to add more heating medium. So this is not a cooling heat exchanger, it's a heating medium exchanger. So adding more of this heating medium through it, it means that the bottom product that's in actual fact in contact with this heat exchanger, the temperature will increase in that. Okay. And then as the process continues, I mean there's also feed that goes into the column, the level will increase of the bottom product. Okay, so sometimes if the level increases too high, what we need to do is we need to feed off then some of this as the final bottom product. Okay, and the same happens then. Say for instance, if the temperature goes too high, what we'll measure the temperature as above the set point, and with the cascade arrangement, we will then close down on the flow through that heat exchanger. And again, if the level maybe increases in the bottom product, what do we need to do? Eventually we'll open that valve, and we'll have a certain amount of the residue that actually goes to a next process or as a final product. Okay, so on the last control strategy is just on the reflux and the distillate. So the distillate is the feed off then of the top product. So that is The purified, either wise, it can be used as a final product or again it's be sent to a next process if needed. Okay, with this last process implementation diagram, again as I said, to determine if we're going to have reflux, going to the column for further purification or tapping it off then as a final product or a distillate. So we can measure what is the level in the accumulator and that can decide then what do we need to do. But if the temperature inside the column in that cascade arrangement, we can in actual fact look at this temperature. If the measured variable is smaller than the set point, it means that, remember, in the accumulator we're going to have a cooled down feed or reflux. So if you actually add it into the column, it can have a great effect on the whole temperature of the column. So first, by measuring that temperature in the column, we can decide, do I need to reflux it into the column again, okay, for further purification. Okay, so the opposite will happen. So in other words, if the temperature, say for instance, measured on TT1 and then controlled by TIC1, if that measured variable is greater than a set point, it means that the temperature can actually, or the column temperature can in actual fact come a little bit down. So we can then feed back from the accumulator that distillate back into the column for reflux and for further purification. Okay, on the second last slide, you can go and inspect that figure. That figure just shows you that you can actually go and extract different types of final products from a column. Different temperatures, of course. So you will start off with a higher temperature at the bottom of the column at 600 degrees Celsius and then go up, and then the last there is just your liquefied petroleum gas at the top product at only 20 degrees Celsius. So again, you can see that with different levels, different temperatures will actually exist inside the column. And then by controlling this temperature, you can get different products for different users. And then on the right hand side, you can just see some examples of typical distillation columns that you can find in industry. Okay, so you can also go and consult further chapter 15 out of the textbook, Process Technology, Equipment and Systems. And there's certain points here mentioned that you can go and look at especially. But I would say that this PowerPoint or the slides is very important. Then also go and look at the video that has been posted, the YouTube video on my tutor that relates to typically again how the whole distillation process works. Also some valuable information and some animations that's actually done on that video. So please go and look at that. So that's the video on crude oil production in a distillation column.